When you look around your house, you'll find a lot of things that are flat, and those have zero curvature. And then you'll find some things that are round in this sort of roundness, and that has a positive curvature. And then if you look around some more, you'll find some things maybe that have this sort of a shape. All right, so this is what in Calculus 3 you called a saddle point. So let me use some tape to show this saddle point. Kind of hard to get the tape to go on just right, but we're doing okay. All right, so here's my saddle point. So if you look here, you'll notice that if you go this direction, it goes up and down, kind of like this is a maximum. And if you go this direction, then it goes the other way, kind of like it's a minimum, and that's what makes a saddle point. And so that place where you've got a saddle point type of thing, that's called a negatively curved surface. And some interesting things happen if you have a negatively curved surface. So one of the things I'm going to do is I'm going to try and make a triangle on this bit of the bottle that is negatively curved. So if I look right here, there's a positive curvature spot. So I need to try and make my triangle go around that spot. Somewhere in the universe, I have a really good flower base that works great for this, but I can't find it tonight, so I'm afraid you get the bottle instead. So I'm trying to make this tape go as flat as it will go. And now when I get right in the wrong spot, then the tape doesn't want to cooperate. But for most of the space, I can make the tape. I can put on the tape and I can just let the tape do what it wants to do. There, that's where the tape wants to go. And it turns out, we'll talk about why later, that when you put the tape where it wants to go, that what the tape is doing is it's doing a tape version of finding a straight line or a shortest path. And so you'll notice that I almost but didn't quite succeed in making a triangle. It just barely comes together over here, and it just barely doesn't come together over here. So I didn't make this quite. Oh, I guess it does, just barely. But you notice this is a really weird triangle, almost like as weird as that triangle we made on the globe, where you went from North Pole down to the equator and around. Only this one's kind of opposite. You get some really skinny, teeny-weeny angles there. So, something that is negatively curved everywhere and has a constant negative curvature, so that it's the same amount negatively curved everywhere. So this bottle has bits where it's positively curved and bits where it's negatively curved, and this part is actually zero curvature, and you can tell that because you can take a piece of paper and you can wrap it over there, and it doesn't need to either tear or bend. Now once I get to this part, see, I'm going to get creases, and that tells you you're getting curvature. All right. And if I tried to take this piece of paper and make it go around this neck here, it would want to either crease or tear right here at this negative curvature spot. So this is a a thing that has different kinds of curvature on it. So, a rather clever mathematician, whom I'll refer you to online, came up with a way of using crochet to make a model that you could use for investigating negative curvature. So this crocheted bit of stuff is very close to being a negatively curved surface that has the same curvature everywhere. And you can see the negative curvature it comes in all of these frilly bits that are, if I just hold them up, they're going to make saddle points, right? If I just hold it like that, it wants to make a saddle point where it goes up and down. So it's like a minimum going this way and a maximum going that way. And so a thing that is, if you continued this out infinitely far, this would be a hyperbolic plane. So a hyperbolic plane is an infinite, negatively curved surface where it has the same curvature everywhere. And so lines are really kind of weird and interesting on a hyperbolic plane. So I've sewn a few lines in here. And so if you want to look at, say, this one, and you want to say, oh, I wonder if that's really a hyperbolic line. I wonder if that really lies on the shortest path between these 2 points, or if maybe the shortest path goes up here or goes down there. One thing you can do is you can pick these 2 ends of my hyperbolic segment, and you can just pull and stretch them. And you should see that that line just, goes right on the stretchy part between those 2. That's actually kind of a little bit hard to find when you're trying to sew in some lines. And so there's another strategy that you do to find a shortest path, and that is you try to fold it. So if I pick any one of these and I try and fold, this is how I made it. So these were all fold lines. Now, when you say fold, one of the things that's going on with this folding is that you are flattening together the 2 sides so that they line up evenly with each other. So if you want to think about going from here to there on this surface, well, if I tried going off to one side, it would be clearly taking longer. But any path that went from here to there, that stayed on the surface, that went down there, well, that would be clearly a longer path than that one. And because this is a fold, so the front and the back match, you get exactly the same picture on the other side. If you try and go from here to there and you go off this fold line, that's clearly going to take longer. And so you end up with some interesting pictures. I clearly messed up my line there a little bit, but these are some examples of I made this perpendicular. Of course, everything's approximate because you can only get so good with crochet, but so the way that you make a perpendicular, if I say, all right, here I've got a line, and I want to make a line that's perpendicular to that, then what I do is I make a fold where this part of the line matches up with itself on the other side. There. And then you extend that fold to make the other line. That's how you get even angles all the way around. So those are 90-degree angles. You can kind of see how you would measure angles here because you can flatten out a little bit, right? So you could imagine, all right, I'm going to flatten out this little bit and then I'm going to trace it onto paper and extend those out big enough that I can use my protractor on it. So there's some interesting things. These 2 lines, this one and that one, those are parallel. If you think about if this was extending out indefinitely, I'm going to just keep it going. You can see how it's, however close it is together right there, it keeps getting bigger and bigger as it goes outward from this hyperbolic line. Both of these lines are perpendicular to this hyperbolic line. That's a property that you get where these are closest together. And as you get out, they're going to get further and further apart. So they're going to be, they're going to never intersect. They're going to be parallel. And that's an interesting thing, you know. So parallel lines on a zero curvature thing, if lines don't intersect, then they also stay the same distance apart. But parallel lines on a negatively curved surface get further and further apart the further out you go. I also made a little triangle here. So, like with the bottle, it's actually kind of hard to make this fold up to be a triangle because it wants to just go, you know. So if I first started folding like this, and it was like, oh, that's just gonna fold and it's gonna go off and it's not gonna intersect. So this is a pretty small triangle, but if I wanted to measure the angles here, I could. I'd just take a piece of paper on top of, put it on top of it, and I would trace out those lines right there at the intersection. I'm gonna grab me a piece of tracing paper and do this. Okay, so I put my tracing paper on top, and now in order to get an idea of what's going on with these angles, I need to trace out what's going on with those two lines right where they meet. And I'm going to flatten out right here where the next two lines meet. Here we go. I'm doing my best to get a decent tracing. I have to kind of change it up. There we go. There we go. And so now if I want to know those angles, of course I have to have long enough lines to use my protractor on. And so I have to extend the lines out in a way, the direction they would go on the flat paper. Because every time we do this, we're doing tangent lines and tangent planes to this surface. So we actually measure the angles over here where it's flat, and we do that in a way that's tangent to the surface. So it looks like this angle is about 47 degrees. This angle is about 45 degrees. And this angle is about 41, 42 degrees. So my angles in that triangle add up to whatever that is. And so we get different things happening with these triangles because of the shape of this surface. And you can see it even more dramatically with this angle. So that angle, if I was going to just estimate, I would say that's less than a 10-degree angle. And this one is a less than 10-degree angle. And that one is maybe 70 or 80 degrees. So you get quite small angles because of the way things curve around the negative curvature spots. So interesting stuff. So this is one good thing that you can touch and play with to get an idea of what a hyperbolic plane is like. And of course, this isn't a whole hyperbolic plane. This is a little tiny piece of a hyperbolic plane. That hyperbolic plane would keep on going forever. And of course, a real hyperbolic plane would, you know, be perfectly smooth. It wouldn't have the stitches in it. But making one that's more solid is kind of hard. You can only fit so much of it in a space because it gets curvy very fast.